I have just given you a comparison between SU2 and SU3. So SU2 had 3 generators, one of them is diagonal. SU3 will have 8 generators, the lowest non-trivial dimensions of those generators has to be 3 cross 3. Inside that the SU2 algebra should sit in. So you still have one diagonal generator which is coming from the SU2 because this part is sitting inside that. And you also have one more which you can construct. So there are 2 diagonal generators for SU3 algebra. Okay. Yeah. I did find out lambda 8. I just said I want to construct with integers put on it, real numbers, in such a way that the trace is 0, unhermitian. What are the multiple ways you can do? You shouldn't increase just arbitrarily high numbers. I want the numbers to also be low. You are saying I'll put 100, 50. Yeah, not that way. You have to put in with lower number of integers to start with and see whether you can construct it. Okay. With lower integers, I don't think you can do any other way. Can you try it out? Overall negative sign is not a new one. Relative numbers, if you can put something else, but they have to be integers because they are some things which is capturing for me some kind of quantum numbers in some fundamental units and I want them to be integers. If you put in this constraint and you don't want to, the way you are saying is I will put 500, 500 and minus something, right? Yeah, but then you can still see that that will be just a 500 scaling factor out of it. Scaling factor is unimportant. What you have to get is a non-trivial matrix, okay. So you have only 2 diagonal generators in that sense, okay, and the number of diagonal generators for the Lie algebra is what we call it as a rank of the Lie algebras, okay. Rank of the group is also another way of saying. So if I say rank of the group is 2, then you should know that the Lie algebra should have 2 diagonal generators. What does that also mean? If I write a state in the case of SU3, just like I wrote it for SU2, I should be able to write the eigenvalue corresponding to lambda 3, let me call it as M3, eigenvalue corresponding to lambda 8, okay, and you will have some analog of the Casimir operator. Let me not try to say what it is, but definitely the magnetic quantum number will have 2 values depending on lambda 3 acts, it will give you M3, right. Lambda 3 will give you M3 times M3 M8. Lambda 8 will give you M8 times M3 M8. You agree? This is the slight variant which starts happening once you go to the states in the case of SU3. Okay. So many times this M3 and M8 together, they write this as a, is denoted as a M vector. So it is M3 and M8 are the 2 components of the M vector, okay. So if you operate lambda 3 on the M vector, it pulls out the first component. If lambda 8 acts on the M vector, it is a 2-dimensional vector, you get the second component. This is a shorthand notation of right. And this is what we call it as a weight vector. Okay. So the M vector is called as a weight vector. What happens in SU2? SU2 it is just a one component vector because it is only picking up one of the diagonal generator. It has only one diagonal generator. So that is one component vector. If you had two diagonal generators, the weight vector will be two component. If there are three diagonal generators, you will have weight vectors to be three component and so on. Okay. So this is the formal notation. The first non-trivial group is SU3, where you will start seeing that you can represent the analog of your magnetic quantum number by your magnetic vector, where the first component will be like your magnetic quantum number because that is the lambda 3 eigenvalue. The second component will be like the new diagonal generator for SU3. Clear? Diagonal generator, because the diagonal generator's commutator bracket will be 0, right? Because they are diagonal, you can show that lambda 3, lambda 8 is 0. So which means you can write a state to be a simultaneous eigenstates of both lambda 3 and lambda 8, and I am compactly trying to write the lambda 3, lambda 8 eigenvalues as a two component vector. Okay, so this is just a two component vector, weight vector belonging to SU3, okay, belongs to SU3, the two component. Okay, so let me come to the things which I am saying on the slide here. So number of diagonal generators is called rank. SU2 has rank 1, Z component of J is diagonal, and hence we can write the simultaneous eigenstates of Casimir operator in Jz in the case of SU2. There is an analog of Casimir operators, but let me not get into it for SU3. Again you can construct bilinears here also. You can take lambda 1 squared, lambda 2 squared up to lambda 8 squared, and you can show it to be commuting with lambda 3 and lambda 8. But I am just going to confine myself to the magnetic quantum numbers. Okay. So recall your SU2 algebra, where for comfort you define raising and lowering operators, which is Hermitian conjugates of each other. So J1 is Hermitian, J2 is Hermitian, but J1 plus IJ2 is not Hermitian, but J1 plus IJ2, the Hermitian conjugate of it is J1 minus IJ2. These things you know, and we could rewrite the same algebra which I wrote in the beginning for Jx, Jy, Jz, right? You can rewrite it in terms of J plus J minus, and you know, this is a closed algebra again, all this equations together. There is some slight, probably a different in notation from quantum mechanics. There is a 1 over root 2 here. Some books follow without a root 2, but then you will get a twice J3 and so on. So that's a matter of normalization. Okay, this is a normalization I am following. And J3 anyway I have said that J3 will give you, I am suppressing the H cross, I am putting H cross to be 1. So this gives you some M, which is some value which could be half odd integers in the case of SU2, right? For spin J, spin half, it is half. If it is spin 1, it is 1. So it could be integers or half integers. And then the ladder operation will take you from, that's why the definition of a ladder operation. You can prove all these things using this algebra. I'm sure you would have done it as a quantum mechanics course. Here I am just trying to give you the final result which you have learned. Basically, if you take this magnetic quantum number m, the plus raising operator will take it to m plus 1, minus will take the magnetic quantum number m to m minus 1. Okay. So, there are two operators which helps you to go from one state with magnetic quantum number m to m plus 1 or m minus 1. And then this coefficients also can be determined purely from this algebra, and they turn out to be related to j minus m, j plus m. Okay. So, this is something which you all know. I am not going to derive this. My only requirement is that I want you to understand the fact that you had a diagonal generator and then the remaining generators you made it into a complex conjugates of each other, okay, which are off diagonal, but you tried to make it into a complex conjugates. So, this is the theme which is very important in group theory. Okay. So, let me try and say for the SU3 algebra, whatever I said for SU2, there are 8 generators. The explicit form you do not need to memorize, you can write it down on a sheet, to see that lambda 1, lambda 2, lambda 3 is diagonal, and similarly lambda 8 is diagonal. These coefficients are put on purpose to take care of some of the quantum numbers which are seen experimentally. Okay, just like I wrote for the Pauli matrices half h cross, just to take care that the experimental value of the Jz quantum number is half h cross or minus half h cross. Similarly, these coefficients come because of some experimental detail, but as of now, even if you keep this to be some kind of a constant, these are the 8 matrices where lambda 8 and lambda 3 are diagonal matrices. So, the rank of the SU3 algebra is 2. So, I have confined to SU2 and SU3, but whatever I am saying for SU2 and SU3 goes systematically to SU4, SU5 and so on. I hope you appreciate that fact. So, for SU4 you will have how many generators? Somebody? 15 generators, okay, you can check it out, 15 generators, 15 of them, and then how many? Diagonal will be 3 of them. So, you will always have for any SUN n squared minus 1 generator, and you will have n minus 1 diagonal generators. So, the rank of the SUN will be n minus 1. Okay. Okay. So, just like I wrote the up spin and the down spin, okay. So, I am going to do this here for you. The lowest dimension which I am going to write is called sometimes as a defining representations or fundamental representation. So, let me put both the cases here. SU2 SU3, you can have states which is up spin, which you denote it as 1 0, and down spin which you denote it as 0 1, okay, and this is also equal to m equal to half. I am suppressing h cross, this is equal to m equal to minus half, okay. This is SU2. SU3, you will have m1 vector, which I am going to denote it as, what is m1 vector? The two components of the m1, it has two components. First component will be the eigenvalue of lambda 3, second component will be the eigenvalue of lambda 8, okay. Here this m was an eigenvalue of Jz alone or sigma z. Now it will be that it is a simultaneous eigenvalue of lambda 3 and lambda 8. Clear? So M1, M2 and M. Okay, this is what I am calling it as mu1 in the slide. I am calling it as mu1. Let me just follow the notes which I have, mu1, mu2 and mu3. Okay. Now try to find operating your lambda 3 by 2 on mu1. Do that matrix. What will that give you? Half on mu1, right? Are you all with me? Mu1 denotes 1, 0, 0. So the mu1, on the mu1, if you operate this, I am going to use lambda 3 by 2. So you will get a half. Just a convention. This is because of SU2 sits in that, and I am looking at the fundamental representation, which should also have the same half eigenvalue. That is the reason. In fact, all the generators I will scale it like that. Okay. This is just an overall scaling. Should not really matter. What is this going to be? Lambda 8 I wrote somewhere, but then there was also this convention of putting a normalization here. Let's follow that normalization. So tell me what happens here. That will give you okay. So what is the mu1 vector explicitly? Is that okay? So this is nothing but half, it is half root 3 is what I get, right? But this is just a matter of normalization. We'll fix the normalization and we'll get going. What I am trying to give you the fact is that formally I am writing it as a weight vector. The explicit two components of the weight vectors are the eigenvalues of lambda 3 and lambda 8 up to some normalization. If you use that, then you define your mu1 vector to be this. Okay, so this is all I am trying to do. Yeah. Any questions on this? It's fine. Yeah, so one way of seeing is that if you square this, you do get 1 plus 1 plus 4, which is 6, right? So I have to put a root 6 and then I also have another half coming up. So there's some reason which is put in, we'll come to it. Or another way of saying is I want to get my proton charge to be plus 1. You understand what I'm saying? If I want the proton or an electron of course is fundamental, it is not going to be a composite which is going to be by tensor product. If I want my proton charge to be convention with my experimental evidence, I need to fiddle around with this normalization constant, and Gelman has put in these things. Okay, so I am not doing anything. Okay. This is good. Okay. So the three basis states of the lowest non-trivial representation of SU3 algebra, which is called also as a defining representations. Okay, all these things which I am writing are sometimes called in the literature as fundamental or defining representation. Okay, so fundamental or defining, that is the lowest non-trivial representation. For SU2 it is 2 cross 2, SU3 it is 3 cross 3. Okay, so let me just try to say what I am trying to put in here. This lambda is analog of your quadratic Casimir, we will come to it at some point. Mu1 is boldface here, which refers to two component vector in this context, and explicitly the corresponding basis state in the three-dimensional vector space which I take is just the usual one, 1 0 0 0 1 0 and 0 0 1. Corresponding to this, you try and find out what are the eigenvalues of lambda 3 by 2 and lambda 8 by 2, and you can show that the mu1 vector is nothing but half comma root 3 by 6, which I have explained it now, but you can show mu2 will be minus half. A minus half is coming because of this, and root 3 by 6, and the last one mu3 has 0 as the first component, and the second component is minus 2 by 3 by half, so it is minus 1 by root 3. So that is what we get as minus root 3 by 3. So these are the analog of your magnetic quantum number. In the case of spin half particle, the magnetic quantum number, there are two values, minus half or plus half, or my down state and up state. Now you have three fundamental states, okay. There are three fundamental states, and this is what he attributed to saying that nature has three fundamental quarks. He called it as U quark, just like this is called as up spin and down spin, okay. He called it as U quark, which is also up quark, down quark and strange quark. Strange quark, okay. So each one is a is that clear? So there are three fundamental states of SU3 which is attributed to, and the corresponding values are going to give you something which is physical, we'll come to it, but there are two diagonal elements, so you'll have two eigenvalues which is put together, which is called as a weight vector. Okay. So I have drawn it also for as a diagram the three fundamental states. This blob, the circle, is what we call it as a up quark state. Another one is called as a down quark. Basically, it's a coordinate in the weight vector space. Okay, weight vectors has two components. That's why I'm drawing a two-dimensional plane. If it was SU2, what is the situation? SU2 does not have the second one. So this one is not there, and only half and minus half. The second component will not be there. Is this clear? So is the weight vector concept clear? That you, as you increase the number of diagonal generators, the weight vector diagram will become 3-dimensional, 4-dimensional, and so on. But at least algebraically I can write down the plotting I could do this way. Definitely for SU3 in a 2-dimensional plane, the axes are the H1 eigenvalues and the H2 eigenvalues, and H1 and H2 I am calling lambda 3 by 2 as H1 and lambda 8 by 2 I am calling it as H2. Okay, this is the notation. Fine. Yeah, so see, the thing is, most of your protons and neutrons were conventional. Then they started seeing new particles and they wanted to give some name to it. And then they said, oh, it will involve some new exotic particles, and they probably called it strange. Okay, so that brings me to a summary of what I want to say for the SU3. Okay, just like you had J plus and J minus, J plus and J minus, the role is what? If I do a J minus on this, the m quantum number shifts by 1 unit, plus or minus 1 unit depending on whether I do j plus or j minus. You all know that. So I am going to call that as some kind of a shift which is just a single number 1, and j plus and j minus I will call it as plus or minus alpha. This is a single number in the case of SU. In the case of SU3, what should j plus j minus do? It should take from here to here or here to here, right? And you know that this is a weight vector. I would like to write that as a plus or minus corresponding number which is a 2-component vector. Or in other words, when this acts on mu1, so let's do that. So if you have j plus minus on, let me do it j minus alpha on m will give you m minus alpha. Is that clear? Now I am going to say that E minus alpha on mu1 is going to give me fair enough. A single number is promoted to a 2-component vector for SU3, and then these operations, there we just wrote j plus minus because it was just increasing or decreasing by 1. We didn't even need to put a plus 1. But in general here it could be a non-trivial vector which will take you from mu1 to mu1 minus alpha, and this should be some definite one of these 3 states, because j minus on this will give you this. Similarly, j minus on that should give you one of those states. I will come to it, but this is the formal ladder operator notation